From the screen you're looking at right now to the chips that make it all work, our entire world is built on layers of materials so thin they're basically invisible. But have you ever wondered how you create something that perfect? Well, today we're diving into the incredible science and AI that are being used to engineer these films, literally one single atomic layer at a time.
So, this is the big question, right? This is the fundamental challenge in material science. How in the world do you control a process at the atomic level to create a completely flawless surface? I know, it sounds like something out of science fiction, but today we're going to break down the amazing toolkit scientists are using to make it happen. All right, so before we can jump into the really high-tech simulations in AI, we have to start with the basics. I mean, think about it. When you're juggling variables like temperature and pressure and power, just guessing is never going to get you where you need to be. You need a smart, systematic way to find that perfect recipe. And that's exactly where something called design of experiments, or DOE, comes into play. The best way to think about it is like you're baking a cake. Now, instead of baking 1,000 random cakes to find the best one, DOE tells you, hey, just bake a few strategic ones. You change the flour, the sugar, and the baking time in a really smart, methodical way to find that perfect combination way, way faster. A really popular way to do this is with the Taguchi method. It gives you a clear workflow. First, you figure out your key ingredients, your power, pressure, temperature. Then, you run a small, super strategic set of experiments. The analysis then points you to the single most influential factor, so you know exactly which knob to turn to get the perfect result. And we can see this exact method in action. Check this out. In a study on nickel-chromium films, the Taguchi method made it crystal clear that the sputtering power, not the pressure or the temperature, was the #1 thing affecting the film's quality. This gives engineers a clear, data-driven order. If you can control the power, you control the quality. It's that simple. Okay, so real-world experiments are fantastic, but they do have their limits. You only get to see the final result, not what's happening while it's happening. To bridge that gap, our next tool takes us into a virtual lab where we can ask, what if we could actually watch the atoms collide? This comparison just lays it all out. Real experiments, they can be slow, they can be really expensive, and they only tell you what happens in the end. But virtual simulations, using methods like Monte Carlo, are lightning fast and show you how it happens, right down to the individual atom. It's like having an atomic-level slow-motion camera. So what are these simulations actually telling us? Well, they're answering the most fundamental questions you can ask. Things like, how many atoms are actually getting knocked off the target material? How are they interacting with each other? Where is all that energy going? This isn't just about the final product. It's about getting a deep, intuitive understanding of the physics of the process itself. So we've found our best recipe and we've simulated the atomic collisions. Now we've got to understand what happens next. How do all those atoms that have been knocked loose actually come together to form a surface? And this right here, this is the crucial part. Everything, and I mean everything, depends on those first few moments. The way the very first layers of atoms land and decide to arrange themselves determines the entire structure and the quality of the final film. It's the most critical foundation you can imagine, just at the nanoscale. Scientists have modeled a few key ways this can happen. The first one is called Volmar-Weber, or you can just think of it as island growth. In this case, the atoms that land on the surface would rather stick to each other than to the surface itself. So what do? They clump together, forming these little islands that eventually grow bigger and merge into one. Then you've got the second mode, known as Stronsky-Krestanov growth. This one is a two-step process. First, the atoms form a perfectly smooth, totally complete layer. But after that first layer is done, they switch things up and start forming islands on top of it. Understanding which one of these growth modes is happening is absolutely key to controlling that final surface. The precision here is just astounding. By using advanced techniques like fractal analysis on data they get from atomic force microscopes, or AFM, scientists can model and predict changes in roughness and structure at the scale of a single nanometer. I mean, that is almost unimaginably small. So far, we've covered statistics, physics simulations, and growth models. Now we bring in the final piece of the puzzle. This is the tool that ties everything together and just turbocharges the entire process: artificial intelligence. The concept, really, is beautifully simple. You take all that data from your real-world experiments and your virtual simulations, and you feed all of it into a sophisticated AI model.
The AI then learns all the complex patterns hidden in that data, and it becomes this predictive powerhouse that can forecast the outcome of an experiment before you even run it. So, why does this matter so much? The answer is one word: speed. Traditional material development can take years and years of trial and error. But by using AI as a co-pilot to predict outcomes and suggest the best settings, you can shrink that development timeline dramatically. It is a complete and total game changer for innovation. Okay, so let's bring this all together. We've just walked through an incredibly powerful toolkit that is revolutionizing how we design and build materials from the atom up. We start with statistical methods to efficiently find the best recipe in the real world. Then we use physics simulations to let us see the unseen atomic level action. After that, growth models help us understand how the film actually builds itself. And finally, AI comes in and integrates all of that knowledge to predict the future. Each tool builds on the last one, creating this amazing, comprehensive system for designing materials. And this brings us to a really fascinating final thought. Right now, these tools are being used to optimize materials we already know about. But what's the next step? What happens when an AI, armed with all of this data and understanding, can go beyond just optimization and start inventing entirely new materials with properties we haven't even dreamed of yet? That's the future we're building, one perfect atomic layer at a time.